for giving me a chance to talk here. Okay, this work is done as a joint work with Suho at University of Michigan when we were both in the graduate school. And most of this talk will be, okay, I apologize first, but most of this talk will be a combinatorial. So I will, there might be some things that people are not very familiar with, so I will try to go slow and explain things carefully. So please interrupt me anytime if you have any question. Okay. Okay. The goal of this problem is to link Schubert varieties with hyperplane arrangement. I will explain what Schubert varieties and which hyperplane arrangement we are interested in a little bit later. Okay. Okay, here it is. So we are going to link this Schubert varieties on the left-hand side with this something called inversion arrangement on the right-hand side. They are both parameterized by this element of Weyl groups. If you are not familiar with Weyl groups, then you may think of this as a symmetric group, permutation group. That's the simplest case called type A case. Schubert variety naturally has this cohomology structure, and it gives us a polynomial called Poincare polynomial. On the other side, if we have a region, hyperplane arrangement, we have these regions. Regions are those connected components of this complement of this hyperplane arrangements. And if we count regions carefully, we can have this polynomial called the region polynomial, RWQ. And Poincare polynomial evaluated the number 1 gives us the number of elements in this Bruhat order, Bruhat interval between identity element and the element we are looking at. I will explain this a little later again. And our region polynomial evaluated at the number 1 gives us the number of regions in the hyperplane arrangement. Our first theorem, okay, here Postnikov appears as well, but so we three proved this for type A case at the first, and Suho and I proved for the other cases later. Okay, our result is that these two polynomials are equal if and only if this Schubert variety is rationally smooth, something called rationally smooth. Probably you're more familiar with the concept rationally smooth than I am.
What's the definition of rationally smooth?
Okay, I'll explain shortly. That was the introduction. So the project is to prove this theorem that two polynomials coincide if and only if this variety is rationally smooth. And we want to describe this hyperplane arrangement and the region polynomial more explicitly combinatorially. And using these tools, we want to factorize this Poincare polynomial into Q numbers when the W is rationally smooth. I say W is rationally smooth when this corresponding Schubert variety is rationally smooth. Okay. And tools to prove these things is essentially the combinatorics of coset groups, of Weyl groups, especially the parabolic decomposition and something called BP factorization of the Poincare polynomial. I will explain briefly later. And other tool we may use is some more combinatorial things, something called signed graphical arrangement. Okay, I'll define signed graph and show how to use this. to understand this picture. And for type A case, the signed graphical arrangement reduces to just an ordinary graph case. And there we can use chordal graphs and perfect elimination ordering. Okay. Schubert variety is the most famous and one of the most famous singular algebraic varieties. Okay. It appears in Kasdan-Lussig theory and Hilbert 15th problem, which is essentially the Schubert calculus. Okay. Its definition is like this. So given a semi-simple algebraic group and its Borel subgroup, the Schubert variety is a closure of the Borel group orbit. It's very simple definition. It is parameterized by this element of Weyl groups. When this algebraic group is type A, something like a special linear group, then this Weyl group becomes the permutation group. Rationally smooth means roughly saying that there's a local Poincare duality. So local cohomology has a Poincare duality at each point. And for simply laced case, okay, simply laced case means the Dynkin diagram has no multiple edges. It's type A, D, and E. Okay. For those simply laced case, rationally smooth is just equivalent to this smooth. Okay. And Bruhat order. Bruhat order on the Weyl group or Cosetter group is a partial order between these elements of this group, Weyl group or Cosetter group. And U is less than or equal to V if some reduced word of U is a substring of a reduced word of V. Now I'll just show you an example. For instance, if V is S1, S2, S3, S1, okay. SIs are the simple generators of the Weyl group. So for permutation group, SI is just a transposition between I and I plus 1 number. Okay. So if we multiply these generators, we get an element B. And if U is something like S2, S1, then it is a substring of this reduced word of V. So in this case, U is less than or equal to V. Okay, this is reduced word means this number of simple reflections appearing in this word is the smallest. We cannot reduce more. It is already reduced. Okay.
So this is some simple
Okay.
not reduced.
For instance, if V is S1, S2, S3, S1, S3, then S1 and S3 commutes because S1 exchanges 1 and 2, X3 exchanges 3 and 4, so this exchange commutes, so we can rewrite this as, okay. S3, but S3 times S3 cancels out, so this becomes this. So this is not a reduced word. Okay. So so this is a very famous partial order on the Cosetter group, Weyl group, or permutation group. Okay. Okay, and oops. Okay. And this Poincare polynomial of a Schubert variety is, by definition, it's a generating polynomial of this dimension of the cohomology. But for convention, we just look at even degree cohomology because all degree all vanishes for Schubert varieties. Okay? And there is a very well-known correspondence between cohomology structure and this Bruhat order. This is called strong Bruhat order. And that the interval between identity and W means those elements smaller, less than equal to W in this partial order. This correspondence is namely the Poincare polynomial is just a generating function of this Bruhat interval. So if we sum over all the elements less than equal to W under this Bruhat order, and Q to the length of the U, we get the Poincare polynomial of the Schubert variety, XW. So that this is a very well-known fact. And theorem of Carr and Peterson says the Schubert variety is rationally smooth if and only if this Poincare polynomial is palindromic. Okay, what is palindromic? What does this palindromic mean? Palindromic means these coefficients appearing in the polynomial are symmetric. So like something like Q squared plus 2Q plus 1. If Poincare polynomial is like this, then coefficients are 1, 2, 1. It's symmetric from if we read from the left or read from the right, it's the same. So this is called palindromic property. And if Poincare polynomial is palindromic, then the Schubert variety is rationally smooth and vice versa.
Why is that meaning of palindrome?
Well,
Why did this called maybe symmetric or not?
well, because symmetric polynomial has another meaning. Symmetric polynomial is just symmetric. Yeah, that may confusing. That may be confusing. Yeah. So it's not a difficult thing as it looks. Okay. So okay. So so this theorem gives us a way to avoid algebraic geometry of rationally smoothness. And just you can look at the combinatorics of this Bruhat structure.
So you explain a little bit explicitly the generating function of the input?
Oh, that's just so. Okay, I'll give you an example shortly. Here, this is a Bruhat partially ordered. Bruhat order structure of S4. So permutation group of 4 elements. And okay, if we look at this identity element, okay, the Poincare polynomial is just 1. Okay, this is a better example. If we take this 2, 1, 4, 3, then the elements less than equal to 2, 1, 4, 3 are this, and this, these red guys. So, and these are graded by length. So the Poincare polynomial is Q squared plus 2Q plus 1. Q to the length grading plus, okay, we sum up all the Q to the length of the elements.
Length means the number of cycles?
Number of, yes, number, okay, the length of the reduced word. Yeah, this. Okay, so this is palindromic. This is rationally smooth. If we look at 3, 4, 1, 2, then these red guys are all the, this is the Bruhat interval. And Poincare polynomial is not palindromic. So 3, 4, 1, 2 is not rationally smooth. If we take the longest element, it's always palindromic, and it is well known that it's rationally smooth. But it is smooth, and in type A, smoothness is just the same as rationally smooth. So, okay, this is the other object. we want to see the inversion hyperplane arrangement. Oh, oops, arrangement, not arrangementa. Okay. And okay, we have a vial group. So, okay, vial group. Okay, we have a root system. For vial group, we have a root system. So for type A, the root hyperplane arrangements are those just a collection of all the hyperplanes defined by this simple equation. This is the root hyperplane arrangements for type A, and the symmetric group permutes all the regions of this hyperplane arrangement. There are n factorial regions. Okay. And this inversion arrangements is just take all the okay, for root hyperplanes, these hyperplanes correspond to some reflections, and we only look at those reflections that reduce the length when multiplied to this W. Okay, I will give you an example shortly. Okay, and this is the inversion arrangement. This is by definition subarrangement of this root hyperplane arrangements. This is called cosetal arrangement, and this is the inversion arrangement of the longest element W0. And okay, I will not explain this deeply, but this is related to some other partial order called weak Bruhat order. Although it shares the name with strong Bruhat order, they do not have much connection. I mean, there's not very many things that relates this strong Bruhat order and weak Bruhat order. Okay, and region polynomial is just the Q analog of the number of regions. It's okay, I'll explain this. So we fix one region, R0. And this dr, R0 means it's the number of hyperplanes we have to cross to go from R0 to other region R. Okay. And we sum up Q to the D, this distance for all the regions. Then we get a region polynomial. So if we plug 1 here, then it gives us just the number of regions. This region polynomial is always palindromic, unlike the Poincare polynomial. Okay, here's an example. For type A2, this the vial group is S3, the permutation group that permutes 3 elements. And this is the root hyperplane arrangement. So I labeled each region with the elements of the permutation group. And if we take the longest element 3 to 1, every hyperplanes are inversion hyperplanes of this element. So this red guy is, the entire hyperplane arrangement is inversion hyperplane arrangement. And from this region 1 to 3, the identity region, this is the distance from the identity region to this region. 1, 1, 2, 2, 3. So the region polynomial is Q3 plus 2Q squared plus 2Q plus 1.
So the blue number means the distance?
Yes, distance from this identity region. Okay. If we take 3, 1, 2 instead, then only these 2 hyperplanes are inversion hyperplanes, because if we cross this hyperplane, the length decreases. And if we cross this hyperplane, length also decreases. But if we cross this gray hyperplane, length increases. So this is not the inversion hyperplane, so we erase it. And only these two remains. And this is the identity region. Okay, this is the region that contains identity elements. And this is the distance. So region polynomial is q squared plus 2q plus 1. Okay. There are some known results about the relation between these two objects. The well-known result is that for longest element W0, Poincare polynomial and region polynomial are just the same. That's just obvious thing, because for the longest element, inversion hyperplane arrangement is just the entire root hyperplane arrangement, so it's almost obvious. And there is a well-known formula of factorization of this Poincare polynomial for the longest element. It is well known that it factors into product of q numbers. Okay, here q numbers are for example, q number of 3 is q squared plus q plus 1. So if we plug 1 in q, we get 3. It's a q deformation of natural number. And it is well known that Poincare polynomial of the longest element factors into q numbers. Okay, for type A, Lakshmibai and Sandhya proved that this Schubert variety is smooth, equivalently rationally smooth, if and only if W avoids these two patterns. Okay, so again, I have to explain pattern avoidance, but maybe I can skip. Okay, so and Holtmann, Linusson, Scherchen, Gerstrand proved that these two polynomials evaluated at 1 coincide if and only if W avoids these patterns. And you can see that, okay, 4, 2, 3, 1 appears here. And, okay, I have to explain it anyway. So 3, 4, 1, 2 appears in these patterns. Okay, for example, 3, 5, 1, 2. 3, 5, 1, 2 appears in here. And that's just relatively the same as 3, 4, 1, 2. So that means this contains 3, 4, 1, 2. And if W avoids these two patterns, it has to avoid these 4 patterns. And so for smooth Schubert variety, we know that Poincare polynomial and region polynomials are the same when evaluated at number 1. Okay, some other cases. Sarabili gave a similar criterion of this for, this is not smooth, but rationally smooth. So rationally smooth criterion for classical types ABCD. And Holtmann gave a similar criterion of this for all finite cosetter groups, not only Weyl groups. Okay. And our theorem says not only at this 1, these two polynomials are actually equal when the Schubert variety is rationally smooth. Okay. What does it mean? For longest element, okay, here's a demonstration again. For longest element, we have entire Bruhat order, and we have entire root hyperplane arrangements. So Poincare polynomial and region polynomials are given by this. And for 3, 1, 2, we have only this part and this part. Okay, so polynomials are like this. But this is a taking lower interval of a strong Bruhat order, while this is taking a contraction of a weak Bruhat order. Okay, weak Bruhat order is just this blue. You can just think of a weak Bruhat order as this just blue graph. So this is taking a contraction. We contracted these two vertices as a one. So our theorem says there's a mysterious relation between taking this truncation of a strong Bruhat order and taking a contraction of a weak Bruhat order. That was rather unexpected. Okay, here's a proof idea. Proof idea uses a well-known, not well-known, but uses the factorization of a Poincare polynomial. So for rationally smooth Schubert variety, we have some nice factorization, a nice decomposition of Algebra element, and Poincare polynomial factors analogously. And we show that this region polynomial also factors in the same way. So, and we can use the induction. That decomposition is called BP decomposition. It's Billy and Posnikov. So it's a kind of parabolic decomposition. So for a Weyl group, we have a Dynkin diagram. And in type A case, it looks like this chain. And J is a leaf removed subset of this Dynkin diagram, so something like this. This is a J. Okay? This is a leaf of this graph. So we remove one leaf and remaining part is J. And we take a parabolic decomposition with respect to this J. And if that decomposition satisfies this property, that U is a unique maximal element in this parabolic group below W, then it's called BP decomposition. It's a kind of a complicated combinatoric stuff. You can just think of it as a black box. Okay. And theorem of Billy-Posnikov is that if W is rationally smooth, then it has a BP decomposition. And if it has a BP decomposition, then the Poincare polynomial factors. PW equals PU times this quotient PV. So, and our theorem is when the Schubert variety is rationally smooth, then, and this is the BP decomposition, then region polynomial factors like this. Here, this PV is just the same as this PV, and U has a smaller length, strictly smaller length than W, so we can just use the induction on the length, and we prove the theorem. Okay. There's another way to prove our theorem for classical types, A, B, C, and D. It uses something called signed graph. Signed graph is a graph, so V and E is a vertex and edge set, but here edges, there are three kind of edges: positive edge, negative edge, and half arc. And orientation of positive edge is just the same as the ordinary orientation, the orientation of ordinary graph. But negative edge has different orientation. It's introverted or extroverted. And half arc is just the same as, okay, has the same orientation. And a signed graph is called acyclic if every subgraph has a source or sink. Okay, source means every orientation of the edges connected to this vertex are outward, and sync is inward. And there's a coloring of a signed graph with odd number of colors. So if two vertices are connected by an edge E, then it has to satisfy this condition. So if they are connected by a positive edge, they have to have different colors. If they are connected by a negative edge, they have to have different color by the sign. Okay. So if it is connected by a negative edge and one vertex is colored by number 1, then the other vertex has to be colored other than negative 1. And a vertex is connected to a half arc, then the color has to be different from 0. This is the condition. And given a signed graph G, this signed graphical arrangement is the collection of hyperplanes defined by these equations. So it's similar to this root hyperplane arrangement. It's a little bit general. Okay, this first part is just the root hyperplane arrangement of type A. If two vertices are connected by a positive edge, then we attach this hyperplane. If two vertices are connected by a negative edge, we attach this hyperplane. Okay, if we have a half arc, we attach this hyperplane. So given a signed graph, we have a hyperplane arrangement. And theorem of Jastrzębski says that number of regions of this arrangement is the same as the number of acyclic orientation of the signed graph G. And the chromatic polynomial of this signed graph, we define the coloring of a signed graph, so there's a chromatic polynomial. That's not that obvious, but it's a theorem. And this chromatic polynomial, okay, so chromatic polynomial means it gives us the number of way to color the graph with T colors. Okay. And chromatic polynomial coincides with the characteristic polynomial of the hyperplane arrangement. And characteristic polynomial of a hyperplane arrangement is just some polynomial that encodes the information of intersection lattice of the hyperplane arrangements. Okay, intersection lattice is the partially ordered structure of all the intersections appearing in the hyperplane arrangements. The order is just inclusion.
T is 2 is plus 1.
Yes.
So, for example, T equals 1.
Yes.
So it means the number of coloring will be just one color.
Only 0.
Only 0.
Yeah.
So 0 means the one color.
Yes. So okay, coloring is from negative T to T. Oh, okay. No. Negative S, yeah. Negative S to S, and T is 2S plus 1. Okay. Okay. An inversion graph of classical types. For classical types, A, B, C, and D, we can represent each element of a Weyl group as a signed permutation. For type A, it's just a permutation, as we've seen here. But for example, for type B, it's a signed permutation. So it's a permutation of numbers with these signs. So we permute the numbers and give some signs to each number. I'll show you an example. Okay, so for text set is 1 to n. And so each element is represented as signed permutation, and we connect I and j with positive length, positive edge if wi is greater than wj. This is just the same as type A case.
So what is wi? Wi is the natural number or just plus?
Wi is a number between negative n to n except 0. So for example, in type B, type B 2, for example, oh, yes, 3, then it's a permutation of 1 to 3 plus the sign. So, for example, 3, negative 1, 2 is an example. We permute the numbers and attach signs to each number. And this is W1, W2, W3. Okay. And connect I and j if Wi is greater than Wj. Connect with positive edge. And connect with a negative edge if Wi plus Wi is less than 0. Oops. I'm sorry. This was type A and for type A and D case. For type B, we also have half arc. If Wi is less than 0, we attach a half arc. Then this becomes an inversion graph. For type A, this second part doesn't matter because for type A, Wi's are always positive, so this second case never appears. So the inversion graph is just ordinary graph. Consists of positive edges. Yeah. And for given this inversion graph, we take the inversion graphical arrangement, signed graphical arrangement of this inversion graph, then that's the inversion arrangement of this element. So all reduces the combinatorics of this inversion graph. And region polynomial is generating function of acyclic orientations of this signed graph, inversion graph. Here's an example. B2, this is 1, negative 2. I wrote negative 2 as 2 bar. Here, this is an example of a file group of elements B2. And this is the inversion graph because 1 is greater than negative 2, so we connect with a positive edge. 1 plus negative 2 is less than 0, so we connect with a negative edge. And negative 2 is less than 0, so we connect a half arc. This is an inversion graph, and this is all the set of acyclic orientations on that graph. And this is, we can form a ranked poset with these acyclic graphs. And this is a strong Bruhat order. And RW, the region polynomial is just, and Poincare polynomial are just q squared plus 2q plus, q plus 2q squared plus 2q plus 1. They are the same. That's the demonstration. Okay. Using this graph language, for type A, we can do something more. Using this Lakshmi-Bar-Sandhya's criterion on type A, smoothness criterion in type A, it's smooth if and only if W avoids pattern 3, 4, 1, 2, and 4, 2, 3, 1. But in the graph language, this implies that the graph is a chordal graph. Okay, chordal graph means if we have this full cycle, something like square in the graph, then we have to have a diagonal between at least one diagonal. That means chordal graph. And if W avoids these two patterns, that the inversion graph has to be chordal. And there's a nice ordering of vertices for Corder graphs. And using this, we can calculate the chromatic polynomial very easily. Okay, here's an example. This is a Corder graph, and this is the perfect elimination ordering. And exponents of this graph is at each vertex, the number of edges going left. So 0, 1, 2, 2, 3, 3, 1 are exponents. And the chromatic polynomial is just the product of t minus the exponents. Okay, and we've seen that this chromatic polynomial coincides with the characteristic polynomial of the hyperplane arrangement, inversion arrangement. And our theorem, another theorem, is that for type A, the Poincare polynomial factors into Q numbers, and these Q numbers are exponents plus 1. And for the longest element, this is a well-known result. Okay, we can rewrite this like this. So Q number of EI plus 1 is 1 plus Q number of EI times Q, because of this definition of Q number. And okay, the reason I rewrite this is going to be clear shortly. And there's another object, CW, geometric object called CW. That's the complement of the hyperplane arrangement. So hyperplane arrangement is a collection of hyperplanes. We union all the hyperplanes and tensor with the complex field and take the complement. Then that's another geometric object, and we can calculate the Poincare polynomial of that guy. Then the Poincare polynomial is the product of 1 plus EIT, where EI is just the same exponents. So if we compare these two, this is the Poincare polynomial of Schubert variety, XW. This is a Poincare polynomial of this complement of the inversion arrangement. And they look very alike. Is there any geometric meaning for this? It would be very interesting if we can find one. Okay. And there are some conjectures and questions. We proved that these two polynomials coincide for when rationally smooth for all the vowel groups, but there are something more general than vowel groups, which is a crystallographic Cosetter groups. They include affine vowel groups, something like something related to affine Grossmanian and affine permutations. For them, we have to a little bit modify this definition of region polynomials, but we conjecture that they are the same if and only if the Schubert variety is rationally smooth. And for all finite Cosetter groups, we've seen the Holtmann results that for all finite Cosetter groups, these two polynomials are the same when we evaluated at number 1. So, and this all finite Cosetter group also include all vowel groups in more general. So we conjecture that they are the same if and only if the Poincare polynomial is palindromic. And furthermore, okay, so this result, this factorization result is for type A, the permutation group. We conjecture that the Poincare polynomial of Schubert variety factors into this exponents when for all types when this variety is rationally smooth. And these exponents are just the root of the characteristic polynomial of the hyperplane arrangement. This question is actually related to some old conjecture of some people, including Vic Rayner, that the characteristic polynomial of some large class of hyperplane arrangement factors into linear terms, and so its roots are natural numbers, and the region polynomial of those hyperplane arrangements factors like this, product of q numbers of exponents plus 1. That's a bigger conjecture, and this is a small example of that conjecture. And question, we've seen that the Poincare polynomial of Schubert variety and the complement of the hyperplane look very alike. Is there some deformation of Orlik-Solomon algebra? This Orlik-Solomon algebra is an algebra whose Hilbert series becomes a Poincare polynomial of the CW. And is there any deformation of this guy so that that realizes some polynomial, 1 plus q number of exponents times t? So if we set t equals q, it gives us a Poincare polynomial Schubert variety. If we set q equals 1, it gives us a Poincare polynomial of the complement of the hyperplane arrangement. That would be really interesting if we find one. Okay. Thank you for your attention.